This is section 5.3, Independence and the Multiplication Rule. In this section, our objectives are to identify independent events and use the multiplication rule for independent events, compute at least probabilities, and solve general real-world probability problems. So in our introduction, we're going to first talk about the multiplication rule. Remember last time it was the addition rule. This time it's the multiplication rule. And it is only applicable to multi-stage experiments. There must be more than one trial. So this isn't randomly select one ball from the urn or randomly select one person from the group. This is where you'll select more than one. And you're interested in the probability that the first one is this and the second one is that, whatever. And that's how we'll talk about it. But it could be more than one. It's more than one trial. Could be two, could be more than that. In multiplication, the key word is and. The probability of A and B means the probability that A occurs on the first trial and B occurs on the second trial. Multi-stage experiment, more than one trial. So let's look at an example. We have an urn that contains 3 purple balls, 2 blue balls, and 4 green balls. We're going to randomly select 2 balls, one at a time. Find the probability that the first one is purple and the second one is green. So, what do we need to know? Let's think about this. Probability that the first one, I'm going to use capital letters, P for purple and G for green. So imagine the experiment. You're going to reach into the urn, pull out a ball, record the color, and then you have to take out a second one and record the color. And what's the probability that the first one is purple and the second one is green? Well, we have to define our experiment. After you pull the first one out, what are you doing with it? Do you put it back in the urn or do you put it down on the table? So we have to look at both possibilities. So the first thing we need to know, or the first condition would be, what we would do is run this procedure with replacement. What does that mean? That means you take the ball out, you record that you got a purple, and then you put it back in the urn. Okay, so to find the probability with replacement, if that's our procedure, the probability of purple on the first trial and green on the second trial will be equal to, this is the multiplication rule, so we'll multiply because it says and on a multi-stage experiment, the probability of purple. Well, first, what do we know? We have 3 purple balls, so we have 3 out of, well, we need our relative frequency, relative to the total. What was the total? 3 plus 2 is 5, plus 4 is 9. So we have 9 balls total, so 3 over 9. That's the probability of a green. Times, now we do the probability, I'm sorry, that was probability of a purple. Now probability of green, and we put the first ball back. So there were 3 purples out of 9. There are 4 greens, and because we put it back, there's still 9 in the urn. So then we can multiply for, well, this is a simplified fraction, or 12 over 81, 4 over 27, but we'll just go now to a decimal. by dividing 4 by 27. Let's see what would change if we do this without replacement. What that means is we take one ball out, we record the color, we do not put it back. The probability of purple and on the first trial and green on the second trial. So the first purple, that doesn't change, right? There's still 3 purple balls out of 9 balls. But you do not put the purple one back. So now there's still 4 greens, but there's only 8 balls in the urn because you did not put the first one back. This simplifies to 1/6 or the decimal 0.167. So we do get a different result. Knowing how the procedure is run is important because you will get a different answer. Well, those were 2 different colors. Let's just for interest's sake find out what the probability. Let's do another with replacement procedure. But this time, let's find the probability that the first ball is blue and the second ball is blue. Okay, with replacement, well, the first ball, how many blues did we have? 2 out of 9, but we put the first one back, so we still have 2 out of 9, which is 4 over 81 or 0.049. Now let's see what happens if we conduct the same experiment without replacement. So after the first blue ball comes out, without replacement, let's see if I can fix this. There we go. Without replacement, now it's still, we start with 2 blue balls out of 9, but now there's only 1 blue ball left and there are only 8 balls left. So notice the difference between this one and the A and B, or at least part B. We saw here the denominator changed, but not the numerator, because we still had 4 green balls. But here, with the same color, not only did the denominator change, but also the numerator. So here we got 1 over 36, or 0.028, a different result. It depends on how you perform the experiment. So, when we conduct a procedure without replacement, the probability of the second event is affected by the fact that the first event occurred. The probability of the second event is affected. It changes from what it would have been with replacement because of the first event.